Hi everyone, so today we look at some DC machine examples, and first off we're going to look at a 20 horsepower 230 volt 1150 rpm shunt motor having 4 poles, 4 parallel armature paths, so you can guess what the kind of winding is, wave winding or lap winding, 882 armature conductors. The armature circuit resistance is 0.188 ohms at a rated speed and rated output volt. At rated speed and at rated output, the armature current is 73 amps and the field current is 1.6 amps. We have to calculate all of these things. Now, one of the things you might be wondering at this point is what is horsepower, HP. So horsepower, 1 horsepower is equal to 746 watts. So it's just a straight conversion from watts to horsepower. So if you're on 20 horsepower, 20 multiplied by 746, and that will give you the power of the motor. And the horsepower refers to the final output power of the motor after the friction and windage losses and so on. This is the power available to the user. So to get started, we're going to look at finding the electromagnetic torque. So we're going to look at here TE omega m is equal to EAIA. This is what we're going to use. We have the diagram of the motor here. We have the field winding. Now I've just separated the resistance from the coil. The coil here has no meaning in the circuit. I just put it in so that you could see it's a winding, but the only important thing is the resistance here, RF. And we have in the shunt configuration, so in parallel we have the armature resistance and the motor, the EA, the back EMF. So we know TE omega m, which is the electromagnetic power, is equal to EAIA, which is the electric power delivered from the source. So what we need to do now is we need to find TE by getting these values. So we know IA is 73 amps at full load. This was given in the question. Just to go back, you'll see here 73 amps. We know also omega m because we know 1150 rpm, but omega, we know n is equal to 1150 rpm. Now we want omega, so we know 1 revolution is 2 pi radians, so 1150 multiplied by 2 pi would be the number of radians per minute, and then I divide that by 60 to get radians per second, which is omega. Then I need to find EA. I don't know what EA is. I have 230 volts, but that is the value of VT. So I need to find the value of EA, which is this value here. So I know what IA is and I know RA, so I could calculate the voltage drop here. I know VT is equal to EA plus IARA, so EA would be VT minus IARA. I know IA, I know RA. I could just plug these values into my equation and end up with 131.1 Newton meters as the torque. This is again the electromagnetic torque. Next, I want to find the flux per pole. So I'm going to use this equation. And as we said before, we had some of the things already. 4 poles, 882 armature conductors, 4 parallel paths, 1150 RPM, and then I need to also get a value for EA, so that the only thing I would be left to find is phi. So again I could find EA because EA is equal to VT minus IARA, which is here, and then I have my 4 poles, my 4 parallel paths, my N, my Z, and 60. So I plug in all of those things to the equation and I get 12.8 milliwebers as the flux per pole. So you'll see so far it's just a straightforward use of the equations. You have the information, you just have to plug it into the equations that you know. Next, the rotational losses. So to find the rotational losses, what we have to do, remember, we have the electromagnetic power, and then if we look at the power flow of the motor, we have the electromagnetic power, which is EA, IA, or TE omega M, and this is the power delivered to the motor. This is the power that turns into mechanical energy. But then on the way I have some losses in the form of friction and windage, and then I have, after that, I get the final horsepower of the motor, and this was given to me, the horsepower of the motor, which is 20 horsepower. So I have 20 by 746 here, and I know the electromagnetic power because I worked out TE and I also worked out EA. So I have EA and IA. I worked out TE. I have omega M, which is 1150 by 2 pi on 60. So I could work out EA, IA, or TE omega M to get the electromagnetic power, and then I simply subtract the output power from the electromagnetic power, and I will get the friction and windage power here. So let's see what we have. We have here, this is the horsepower by 746, which is the output power is equal to the electromagnetic power minus the friction and windage. So the friction and windage is simply the electromagnetic power, which is, this is your torque by your omega M, TE omega M, minus your output power, 20 by 746, and I get 868 watts. Alternatively, I could use EA, IA, and I have 216.273 by 73 minus the same 20 by 746, and I still get 868 watts. So whichever way you choose to work it, you should end up with that answer. The important thing here to remember is this relationship. From the electromagnetic power, this is the power that is turned into mechanical energy. Some of that mechanical energy goes into overcoming friction and windage. And when we take care of that, the remainder is available to the user. And remember, the word is windage, which is due to the wind or air resistance, and not windage. It has nothing to do with the winding of the motor. Good. So next, the last part, I think it was, we have to find the efficiency. And we know P output over P output plus the summation of the losses, or simply P out over P in, is the efficiency multiplied by 100 to give you it as a percentage. So the P output, again, 20 by 746, which is 14,920 watts, and this is the horsepower rating that you find on the motor. And now we need to find all the losses. So if you remember that diagram, we have the armature, and we have the field. So we have RA, RF, and we have currents flowing here. So we're going to have losses in the armature circuit, we're going to have losses in the field circuit, and then when we convert the power to mechanical energy, we're going to have some friction and windage losses. So these are the three things we need to take into consideration. So we have the summation of the losses, which is the copper losses, the Cu losses in the armature, which is here. we have the Cu, the copper losses in the field, and we have the friction and windage, which we just calculated. So we have Ia squared Ra, which is the power losses in the armature, If squared Rf, and you'll remember I think the current was 1.6 amps, and the friction and windage, which we just calculated as 868 watts. So when we put those together, we get 73 squared, which is the current here, I squared by Ra. Then we have the current here is 1.6 amps, and we know the voltage across this is the same voltage here, which is 230. So we have 230 by 1.6 plus 868. Now why couldn't we do the same thing here and say 73 by 230? Could we have done that? No, we couldn't, because here we have the voltage across here that is separate from the voltage here. So it's not the full 230 volts across the Ra. So you could have said Vt minus Ea multiplied by Ia. That would also be correct as the power dissipation in the resistor. But anyway, we have I squared R plus Vi plus the friction and windage that we calculated from before, and that gives us 2237.85. So for efficiency, output power over output power plus losses, and that gives us 87%. So the last part, so I guess the previous part was not the last part, is the shaft load. And to get the shaft load, which is the effective torque that we could output, we simply need to use the output power divided by the mechanical speed. So the output power again is, this is the effective load that is available, the shaft torque that is available to the user. Remember, the total torque produced, the electromagnetic torque produced, some of it goes into overcoming friction and windage. And then, so that is some of the torque will be used there. And then the remaining torque is the 20 horsepower. So this is the one that we talk about when we talk about the shaft load. So 20 by 746 over omega m, which is 1150 multiplied by 2 pi on 60. Remember, revolutions multiplied by 2 pi. This is the number of radians per minute, and then we divide by 60 to get radians per second. That gives us 123.9 Newton meters. So on to our next question, or maybe I will pause it there, maybe, and do the next one in a separate video so you can review all independently. I think I'll do that. Okay, so that's the end for this one.